then you have like, you would have like, you're integrating along an interval from A to B, right? And then you partition that interval up, you know, with points, and then you have these subintervals, right? You have these subintervals. And then this is x0, that's x1, that's x2, and so on. And this is xn. And then you choose points in these intervals, and then you evaluate the function at those points. Okay, but if you have a function in two variables, so you've got f that goes from R2 to R, then your domain, this part right here, is not just the number line like that. Your domain is looks more like this. So that's, I'm going to say that's A and B. And then here, this is just, we're just integrating over a rectangle. Let me see here. Okay, so you want to integrate over that region. Okay, so instead of it being just the domain just being a line, it's a region is what your domain is. So what you do is you split this up into like things, and you split this up into sections. I'll do it in a different color here. And then here you got these lines right here, and then over here you've got like this. And so over in this case, remember we choose a point from each there, and we evaluate the function at the point. So here the deal is that you choose a point for each subrectangle. You choose a point, and that's your representative. Okay, and then you can like, so that's what this means right here. You're summing over. So this is like, this means choose a point inside one of these subrectangles, multiply that by the area of that subrectangle, and evaluate the function there, multiply that by the area, and then sum over all of the subrectangles. Okay, so so J goes from 1 to N, that would be these right here. So those 4 would be first, and then these 4, and then those 4, and then those 4. Okay, so that's kind of how that works and what that means. And then you take the limit as these partitions become smaller, 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 smaller. That's technically the integral. But no one calculates it that way. Well, but it's important to remember that. Also, the physical interpretation would be where you have, let's say this is your coordinate axes, like that. And you have some rectangle right here, right? Some rectangular region you're integrating across. But up here, you might have like, it might be like some surface that you're looking at, okay? And so this right here might be like this right here. And so then what the physical interpretation would be this volume of this region would be the integral. Okay, so if the red one is z equals f of xy, would be this surface up here. Okay, and then so then the volume of between this surface and the xy plane would be what the integral is. Okay, you can manipulate different integrals to get different surfaces too. And one of the things that's going to come in later is this Fubini's theorem, which tells you, which basically, here's how you actually do integrals. Okay, here's how you calculate the integrals. And with a rectangular region, you can swap the order of integration. So right here, for example, this one, this means you take this expression here, you integrate it with respect to y, and you treat x as a constant as you do that. Then you evaluate it at the upper minus the lower limit. So you have some other function, maybe in x. And then you integrate that function in x, and then you evaluate it from a to b. Okay? So that's how the integration works. If it's a rectangular region, then you can flip it go the other way, integrate in x first, while you're treating y as a constant. Okay, then plug in b, then evaluate it at b, subtract the evaluation at a. Okay, and then that will give you a function in only y. And then you integrate that one, and then plug those points in. Okay, so if it's a rectangular region, you can switch these like this, just reverse the order, integrate with those. And a lot of the times it's a lot easier to integrate it one way first and then the other. So this way of doing it might be easy to do, but this one might be impossible or hard, okay? Or vice versa. And being able to just switch like this only holds for rectangular regions. You can reverse the order of integration in general regions, which we'll get to in section 15.2, but it's not so simple, and it typically requires graphing the regions to set up the integral or to reverse the order. So just even to set the integral up, it requires, you're typically going to have to graph the region, or at least have an idea in your head of what the graph is going to look like, and then do it that way, okay? But you can't just switch the order. That's going to get into a lot of trouble. Okay, so but we'll do that. We'll cover that in 15.2. So now we're still in 15.1. So let's look at the first exercise on 15.1a. Okay, so number 1 says estimate the volume of the solid that lies below the surface z equals xy and above the following rectangle. So this rectangle right here. Okay, you're supposed to estimate it. Okay, so if we were actually calculating this, it would be much easier, but estimating it, ouch. Okay, so z equals xy, and then we're supposed to reuse the Riemann sum with m equals 3 and n equals 2. Okay, so let me show you what this is going to look like here. So over here, x is going from 10 to 16. So we'll say that's 10, and this is 16. And then y is going from 8 to 12. So we'll say that's 8, and that's 12. Okay, now m is 3. That means that this interval here gets split up into 3 parts, which, to make them equal, it's going to be 10, 12, and 14. Okay, n equals 2 means that you only have 2 parts here, so this is going to be 10 right there. Okay, now this means we're going to be integrating over this box right here. Okay, so that's the x-axis, this is the y-axis. So integrating over this rectangle, and you have a bunch of, you have 6 sub-rectangles. Okay, and now it says here, take the upper right corner of each square. Take the sample point to be the upper right corner of each square. Okay, so for this rectangle here, we're going to use this point there. Okay. So here, this is going to be f of. So let me do this. Let me label these. We'll say this is 1. This is 2. Wait, no. 3, 4, 5, and 6. Okay, so 1, the upper right-hand corner is, what's the coordinates of that point?
12, 10.
Yes, 12, 10. Okay, so you're going to evaluate the function here.
So 12 times 10, 120.
And it gives you 120. So the first one is 120. What's the area?
Area. Of
What's the
like
area
the whole thing.
No, just that rectangle.
2 times by 2, that's 4. No.
Yeah.
Yeah.
Yes, that's 4. So the first thing is going to be 120 times 4. Okay, the second one is going to be this corner here. So that's 12, 12, right?
Mm-hmm.
So that's 140 times 4. The third one
14,
is right here.
10.
So that's 140 times 4. And the fourth one,
14,
whoa.
12.
Yeah, 14 times 12. Okay, I'm going to grab my calculator.
1 times 12. 168.
Okay, good. So that's going to be 168 times 4. And then the fifth one,
16, 10. So 160. And then 16 times 12. That's 192. 192
okay, good.
4.
So you add them, you add all these up. You add all these up. Let's see here, 120. Okay, you guys add them up?
3,408. 3408. Oh, got
Like
the.
3, 6.
I think we got different. Oh, yeah. Okay.
Okay, so now, what the? So now the second part B is using the midpoint rule. So that means you're going to choose the center point of each one, of each of these rectangles. Okay, so for the first one, what's the center point? It's
11, 9,
yeah, so that's going to be 11 times 9.
99.
Yeah, 99 times 4. And then the second one, that's 13 times,
1.
whoa, dang. And then the third one,
It's gonna be
that was one.
59.
Oops, that was the third one.
Mm-hmm.
Ah, I mixed everything up. It's because this weird color is just throwing me off, man. 11 times 11.
11 times 11.
And this one's 13 times 9.
9.
Number 4 is
3
13
times 11.
Oh.
5 is 13 times 9. 15. Oh, yeah. Sorry.
And this is 15 times 11.
7.
Okay, so then, let's see, we add all those up. So
11 times 9.
I got 3120.
Okay.
3,120. Okay. Okay, so that's like the only one that we're going to do that way. The rest of them, we're going to calculate it the normal way, what normal rules do. Let's try that color. Okay, so okay, so like I said before, you look at just this inside part right here. Ignore the dy and ignore this -9 and the 9. Ignore that. Only look at that part. Only look at that part. And what you want to do is you want to integrate this with respect to, and treat y as a constant, okay? I'm just going to copy that down, and I'm also going to put the dy over here.
It's gonna be y squared sine. Oh.
Just yx, because you're integrating in x, so y is a constant. So this is sort of the opposite of partial differentiation.
Whoa.
Okay, and then the integral of cosine would be sine, right? But then the y squared stays there. And you're evaluating it from 0. This is going to be x is 0 to x equals pi over 2 is where you're evaluating. Okay, so we're going to resolve that first before we integrate with respect to y. So if you put a pi over 2 in here for x, you get y times pi over 2. And then here, sine of pi over 2 is 1, so that's just going to be y squared. Now, if you put a 0 in for x, you get 0. If you put a 0 here for x, you get 0. Okay, so that's what you're going to get right there. And you can just ignore those zeros now. And now just integrate with respect to y. So this is what, y squared pi over 4 plus y cubed over 3. Evaluated from -9 to 9. Okay, so if you put a 9 in here, you're going to get something. This is, when you do those two evaluations, you're going to just cancel each other out. So that goes away. And here, you're going to get 9 cubed over 3 plus 9 cubed over 3, which is, what is that? 9 times 3. Well, that's a pretty big number. 81 times 3 is 243, I believe. Is that 46?
Brother Hurst,
Yes.
what happened to y squared pi over 4? How come it went to 0?
Okay, because when you plug, okay, so what happens is, this is, if you plug a 9 in,
Yeah.
and then you're going to subtract and plug a -9 in.
Oh.
But plugging a -9 in is the same as plugging a 9 in, because it's squared.
Okay. I get it. Thank you.
Okay, great. Okay, great. Okay, so the next problem, number 3, we're supposed to calculate a double integral. And here it gives you the rectangle, and it says, and then it has this notation that's integrate over this rectangle here. That's the notation for that. Okay, so so what happens is we have to first decide Are we going to integrate with respect to x first or with respect to y first? And you have to try to think which is going to be the easiest.
The x. No.
The x. The x might be kind of a problem because there's an x there, right? And so, and then there's x up here, so that's like what? So let's do. I think the y is going to be easier. So this right here is the y range right here from 0 to 1. So we'll do y first. Okay, so here we have 8x over 1 plus xy, and then we'll do the x range, which will go from 0 to 8. Okay, so this right here, I've chosen to do the y first because I think it's going to be easier, and I like easier, right? Who doesn't like easier? Well, I think I like easier. Maybe I like hard better. Oh well. So we're gonna go with the y first, which means that we don't do anything with the x for now. We just leave that alone. And we're only looking at that part. Okay. Okay. So what's the interval? So just think of x as being a constant. And the integral of that would be the natural log of 1 plus something like that, right? Now, if you take the derivative of this, then you're going to get 1 over this, right?
X.
Times then the partial of this with respect to y is just a plain old x, where there's an x right there. So we'll put an 8 right there, and we should be okay. Ooh, now I'm thinking, what did I just do? Maybe this is harder. Oh, ouch. Oh, no. And now we're going to evaluate it from 0 to 1. And this is y equals 0 to y equals 1. Okay, because you have to do the limits of integration now. Okay, so
It's gonna be 0.
put 1 in, and that's oh dang, 8 natural log of 1 plus x. Subtract and put a 0 in, and that's 8 log 1, which is 0. Okay, so we just have log, we're just going to integrate the log of 1 plus x. You guys remember the integral of log x? Okay, let's do this. We'll do an integration by parts. We'll let u be log of 1 plus x, and dv will be 8 dx, everything else. So du is 1 over 1 plus x, or dx over that, and v would be 8x. Okay, so the integral becomes uv minus integral of v du. So that's going to be u times v, so that's 8x log of 1 plus x, minus the integral of this one, 8x du, which is this one. Oh, man.
We went back to the...
we end up having to do this anyways. Oh, well. Oh, well. Oh, and we also have to remember this goes from 0 to 8. This is also from 0 to 8. Okay, so this is, if we plug an 8 in, then we get 64 log of 9, and then minus 0. Okay, that's that part. This part here, what I like to do is think, man, I wish there was an 8 over here, right? Because then the 8 could factor out, and those can, and I can integrate that easily. So I just put an 8 there. But then subtract an 8. Like that. Okay, and all of this just becomes 8. Okay, so we have 64 log of 9 minus, the integral of 8 would be 8x, 0 to 8, and this one would be minus 8 log of 1 plus x. Okay, and that's also going to be evaluated from 0 to 8. Okay, so we put an 8 in here, so we have 64 log 9 minus, you put an 8 in there, you got 64, and then put a 0, that's 0. Put an 8 in here, that's going to be 8 log 9. And then you put a 0 in here, you get log 1, which is 0, so that goes away. So it looks like 56 log 9 minus 64. Whoa. Huh, interesting. Okay, and that's not it. So we made a mistake somewhere. Ouch. You guys see the mistake anywhere?
In the first derivative, is it supposed to be 8ln open parentheses 1 plus xy close parentheses plus 8 over 1 plus xy?
This one
don't
here?
know. Yeah. Do you take the derivative of the numerator first and then the denominator? I don't know. Yeah, that one.
Okay, if you take the part, so the idea is to take the partial of this with respect to y, and you should
never
get
mind. Would you have the x then? It'd be 8x ln 1 plus xy.
I think so, because it would be 8 times 1 over this. That would give you the 8 over 1 plus xy. And then the partial of this with respect to y, that's 0, and this is just going to be x. So that gives you the x, I believe. If you plug a 1 in, you get this. If you plug a 0 in, you get that. Okay. Oh, here, I think here it is. Okay, this right here, it should be a plus because it's minus a minus. So that's a plus. So that means this should be 72. Yeah, that works. Okay, so So 72 log 9 minus 64. Okay, that works. Sorry about that. Okay, so that was kind of a challenging one. Maybe if we had integrated in the other direction, it might have been easier. So let's look at number 4. Okay, so here they're saying find the volume of a solid that lies under the elliptic paraboloid and above the rectangle, above this rectangle here. So the first thing that you want to do is solve for the z. That's 1 minus x squared over 9 minus y squared over 16. Okay, so that's what your z is. And also another thing is to verify that for all values between, if x is between -1 and 1, then the most that can be is 1/9, right? And then if y is between -3 and 3, the most that can be is 9/16. And if you add 1/9 and 9/16, that's going to be still less than 1. All right. So all these points are above all the points that are in this rectangle are above the xy plane. Okay, so that means that the volume is going to be just the integral over this rectangle of this function here. Like that. So it doesn't really matter which one you integrate with respect to first. So that means that I will go with respect to x first. So this one. So this is what you're looking at right here. Okay. So if we integrate that with respect to x, we have x, the first period's x, then minus x cubed over 27. Whoa. And then minus x y squared over 16. Just like that. And then x is going to go from -1 to 1. Okay, and then dy. Okay, so you plug a 1 in first. That's going to be 1 minus 1 over 27. And then minus y squared over 16. And then plug in a -1. Subtract and plug a -1 in. But what that's going to actually do when you plug the -1 in is it's just going to double everything. So when you plug a negative, when you're subtracting a -1, so it just doubles everything. So we'll double that. We'll just double it right there and do that. Okay, just for shortcuts. Okay, the 1 minus 1 over 27 is actually 26 over 27. So when you integrate that, you're going to get 26 over 27 y.
In my room.
And then minus y cubed over 3 times 16.
On my bed.
From -3 to 3. Okay. Okay, so again, what's going to happen?
All right. Oh.
Mute your stuff.
Oh. Okay, so what's going to happen is, again, when you, well, you're going to get another doubling, okay, when you're doing the upper and lower limits here. So 26 over 27 times 3. So that's putting this up 3 into there. And then this 3 into here, minus 3 cubed over 3 times 16. And then when you subtract and put the lower limit in, it's just going to give you these both again. So if you can just double it right there if you want. Okay, so what do we got now? This is going to reduce that to 9. And then one of these is going to reduce that out. Okay. So what do we got? We got 26. So you got the 4 out here, and we have 26 over 9 minus 9 over 16. Okay, so if you distribute the 4 in, then you're going to get that. So you go for common denominators. So multiply this by 4, and that's going to be 416. Multiply this by 9. Oh, let's see. So what do you think? You guys get to practice a lot more. You get to practice integration for a lot more, right? That's what this is at this point. Okay, great. Let's look at the next problem. Let's try this dark green. Okay, so find the volume of the solid in the first octant bounded by the parabolic cylinder, z equals 25 over x squared, and the plane, y equals 5. Okay, so it helps to like kind of think about what you have here. So there's the z-axis, and here's the x-axis. So z is 25 minus x squared. So that's going to actually be when x is 0. This is going to be up here at 25, right? It's going to be up here, up this bar here. And then you also have this plane here at 5, so it's going to be cut off right there. And this is going to come down to when x is 5. This is going to come down like that. Okay. So you have this thing coming down. You have this like cylinder right here, like that. And you're only in the first octant, which means that you're bounded by the YZ and the XZ planes also. Okay, so it's just this little kind of quarter round thing. And maybe you want to put this on like your baseboard or something to transition between the flooring and the wall. Okay. That's what that looks like that's for. Okay, so this rectangle here is x is between 0 and 5, and y between 0 and 5. And this is your function right here, 25 minus x squared. dA. Okay, so that's your integral, and now let's set it up. Should we integrate in x first? Just to get it out of the way. Of course. Okay, so we're going to integrate in x first, and what do you get?
25x minus x cubed over 3 divided by 3.
Yes. 25x minus x cubed over 3. And you're going to evaluate that from x equals 0 to x equals 5. Okay, so you put a 5 into there, you're going to get 125. And then another 5 is going to also give you 125 over 3. Okay, now there's no y's, it's just a number. And so if you're integrating this, if you're integrating a constant over an interval, then it's just the constant times the length of the interval. So that's just going to be 5 times whatever's here. And this part is actually, I guess you could say 125 times 3 all over 3. So that's 5 times 2. Oh, 5 times 2 times 125 all over 3. Okay, so that's 1250 over 3, I think. Okay, so that's 1250 over 3. That's a 3 in the denominator. Okay, great. So number 6. This is the last problem from the section. And we're supposed to find the average value of f over the given rectangle. Okay, so first of all, what's the area of the rectangle?
Length times width.
Yes.
Just 14? Or
Yeah,
no?
so the width is 14, the length is 1, so that's 14. So the area is 14. So the average value is going to be 1 over the area of the rectangle. Which is going to be, so it's going to be 1 over 14 times the integral of the function over the interval. Okay, so in our case, it's 1 over 14. Now, we're going to integrate 5 e to the y. Okay, this is the square root of x plus e to the y, so that's x plus e to the y to the 1/2. Okay, so what do you think is going to be easier, integrate in x or y? Integrate this in x or in y? Or maybe that'd be the same. But I'll let you guys choose. Which one do you want to do first, the y or the x?
X.
Okay, that sounds good to me. So x, and that's going to go from 0 to 14, because that's your x right there. And then your y is going to go from 0 to 1. Okay, so integrate this in x. And we're going to get, I think it's going to be x plus e to the y to the 3/2, right? And if we go like that, I think that does the trick. Okay, just double checking. Okay, if you take the derivative of this with respect to x, so you take the partial with respect to x, so you don't have to deal with this e to the y. Okay, so it's only, this is the only place where there's an x, right there. So that means this is coming down 3/2, which cancels with 2/3. And then this is reducing by 1, to 1/2. And then you're multiplying by the derivative inside, which is just 1. So you have, so it's going to be just all that exactly when you take the partial. Okay, so now we're going to put in a 14 first for x. Oh yeah, and then we have to do y after. Okay, so now you put a 14 in for x, and you're going to get, what is that, 10 e to the y over 3 times 14 plus e to the y to the 3/2. Then subtract, and we'll put a 0 in for x. We're going to get 10/3 e to the y. Now you put a 0 in here, you're going to get e to the 3y over 2. Oh dear. And now that's dy. Okay, this looks pretty nasty. Maybe we should have done the other way. It's too late now. We can't go back. We can, but it's easier just to continue on. Because I think we got it. Okay, so e to the y times e to the 3y, so that's going to be e to the 5 halves y. Okay, great. So now we take the integral with respect to y of this. And I'm thinking 14 plus e to the y to the 5 halves. Because when you take the derivative of this, the 5 halves will come down. That'll cancel with this 2/5 that I put there. And this will reduce to 3 halves. Then we take the derivative of the inside part, which the derivative of that is 0. The derivative of that's e to the y, which goes right there. So that accounts for the e to the y right there. Okay, so that's it for that one. This one, you know, the integral is going to be just the same thing. But if you take the derivative here, you get this exactly times 5 halves. So you have to multiply by 2/5 over here as well. And that's going to go from 0 to 1. Y is going to go from 0 to 1. Okay. Okay, so I put a 1 in. This is 20 over 15. Okay, so you put a 1 in, and this is going to be 14 plus e to the 1 all to the 5 halves. Minus 20 over 15 e to the 5 halves. Okay, now you put a 0 in and subtract. So that's going to be minus, you put a 0 in here, that's going to be 20 15 times, that's going to be 1. So that's going to be 15 to the 5 halves. Oh, goodness. And then plus, and here again, that's 20 over 15. E to the 0 is 1. Okay, so that's right there. Oh my goodness. Well, a 20 over 15 factors out of everything at least, right? Okay, this is like weird. That's weird. Okay, this reduces to 10. That's a 7. Let's see, what's 7 times 15? Okay, wow. That's actually right. Okay, so 7 times 15 is 105. So that's 10 over, well, I didn't even reduce it. Wait, I can, let me see here. Okay, so that worked for me. That gave me the right answer in Webassign.